Great, so welcome to the school, and thank you for the invitation. This is the first time I've been here, and it looks like a very nice campus with lots of trees and even more birds. They wake me up at like 5:30 in the morning, but anyway, it's nice to have lots of birds around. And as Rajesh said, ask questions if you don't understand anything, because most of the stuff you can, there are review articles, you can read them and so on, but this is your chance to ask questions on things which you may not understand or whatever. So I was supposed to give 2 introductory lectures on EFTs because there's going to be a whole sequence of lectures on various particular examples of EFTs. So I handed these out on the email, I think. So there's some lectures from Schladming okay, I'm supposed to write lower down, HEP-PH. So from a long time ago, 9606, 222, and the stuff I have on chiral perturbation theory is included in that. And then more recently, there's some Lesouche lectures from 1804. So these are archive numbers of 05, 863, but the Lesouche lectures were like 6 1.5-hour lectures. So I mean, here there's 2 1-hour lectures. I'll just do a brief summary of some of the material. Okay, so we're discussing what's called EFTs, which is a huge topic, essentially because almost everything we know is an EFT in some sense. And the basic idea for an EFT is that you can calculate in a controlled manner to some precision observables without having to know the exact fundamental underlying theory. And already we know this in the case of the standard model because there's new physics, there may be grand unification, there may be DSM physics, but nevertheless, you can still go ahead and calculate things at the LHC. There'll be some small error bar because of the new physics, but you don't need to know what it is to be able to calculate. And in high energy physics, in some sense, the basic ideas which I'm talking about started with probably the Fermi theory of weak interactions, where the weak interactions were characterized by some kind of local 4-fermion operator, and that eventually led to the development of the standard model and where this operator came from by the exchanges of W's and Z's. And the other example was essentially Weinberg. And then related work by Adler and Dashan and Galvan on strong interactions. So Weinberg calculated the pi-pi scattering length in, I think, 1966. And it may be hard for you to imagine what 1966 was like, but nobody had any idea what the strong interactions were. There were no quarks, there were no gluons, there was no nothing. And nevertheless, Weinberg was still able to calculate the pi-pi scattering lengths using ideas from effective theories. And basically, that was the start of chiral perturbation theory, which I will discuss, I guess, starting tomorrow. Then after that, there was sort of some more general operator analysis of weak decays, both for weak interactions and also in the case of unified theories, people wrote down operators for proton decay or neutrino masses and so on, so in the context of guts. And then the more systematic development of this now goes under what's called SMEFT, standard model effective field theory, and Tim Cohen, I think, is talking about this next week. Then there were various models, technicolor models, which were composite models for the Higgs in the days when we didn't know what broke the weak interactions. And this has led to the development, essentially, of applications of chiral symmetry breaking, of a chiral perturbation theory to electroweak symmetry breaking. And this, starting from this, the formulation is what's called the Higgs effective theory, which is, I think Tim Cohen is also going to talk about this next week. And then these are, you might call them classical EFTs, and then some tweaks were introduced. So the next one is heavy quark effective theory. And Matthias will discuss this. And the difference between heavy quark effective theory and these other EFTs is that the fields have a label. So the heavy B quark has a label B sub V, where V is the velocity. And so the Lagrangian and the coefficients and so on can depend on V's. And so Matthias will discuss this. And then what's called NRQED, so non-relativistic QED and non-relativistic QCD, or in general, non-relativistic EFTs. And here, you can think of the hydrogen atom or positronium or something as some electron-positron pair. And they're in some kind of a Bohr orbit, it's basically a hydrogen atom, and they're a bound state moving, and they're non-relativistic, and they're characterized by the velocity. So the fields can have a velocity, but now the velocity can change because the things are revolving around each other. So you have what is called label changing interactions. And another related thing is soft collinear effective theory, which is for, well, as the name suggests, soft and collinear particles. This is for high energy scattering. And this also has label changing interactions. Okay, and I'll draw a line here, so I do not understand EFCs below this line. It's a bit subtle. There's all sorts of issues, and we'll see what happens. Matthias will try and explain some of it, but there's some features about this which I think are still not fully understood, even though it's very useful theory and lots of developments have been done. I mean, especially in SCT for calculating jet cross sections and radiative corrections of the LHC and so on. No, it's just the label changing interactions, and then there are some issues with double counting. Oh, and I should say one of the things with this is that there are both of these, you introduce what are called modes. So in SCT, there are collinear and soft gluons. And in the case of these non-relativistic theories, there are what are called potential modes and soft modes. And the problem, for example, is that you can have a collinear mode which becomes soft. So then there's some overlap between the collinear and the soft, and you have to make sure you don't double count and do subtractions consistently and so on, and things get a bit complicated. Not everybody would agree with what I said. I mean, many people are very happy with this and don't think there's a problem. But I mean, there's ways to deal with it, but I would like to understand it better. Let's put it this way. Okay, so just schematically, if you're calculating some observable, and you have an EFT, and it has the word theory in it, what you want to be able to do is to calculate some results or some calculation, and it will have some error bar. But the difference between a theory and a model is that if you wanted to calculate and get a result which is more accurate, you could, let's say, go to one higher order in the expansion. It may take you a lot of work, but you can calculate and get a better result with a smaller error bar. So it's like a systematic expansion where you can improve on it, at least in principle. Whereas in a model, if the model doesn't work, well, okay, we don't know what's going on. There's no way to put in new interactions and so on. An example would be like the non-relativistic quark model. Well, that's not QCD. It's a model for QCD, and it agrees to 20%, but there's no way to improve on it and include higher order corrections or something. You just keep modeling things with more parameters, but here you have a basic Lagrangian and you can calculate. And so I'm going to write this as some expansion, and I just called it some parameter delta, and this delta is an important quantity. This thing is called is conventionally called the power counting expansion, because you're doing like a Taylor series. And delta is basically telling you what is your expansion parameter, and you can calculate to some order in delta. And depending on the calc theory, what delta is can change. So in the standard model EFT, for example, the expansion parameter would be some momentum or energy divided by m, where m is the scale of new physics. In chiral perturbation theory, delta would be the pion mass over the chiral symmetry breaking scale, et cetera. So each theory has its own power counting parameter, and you'll see people talk about hear people talk about the power counting expansion, and this is what they mean. And if you, as I said, if you want to work to some, delta to the square cube or delta to the fourth, in principle, you can work to any order you want. And it's just gets harder and harder. Maybe call this one. The second is that to any order, delta to the n, there's only a finite number of parameters, or if you want, well, let's just say parameters in the Lagrangian. So we will see that unlike a renormalizable theory, which only has a few parameters, and EFT in principle has an infinite number of parameters, so you might think there's no predictive power, but it does have predictive power in the following sense, that if you want to work to order delta or delta squared or whatever, there's some number of parameters. As you work to higher order in delta, the number of parameters increases, but it's still some finite number, and you can always go calculate more things than parameters, and now you have parameter-free predictions of the theory. And you can compare that with experiment and see if the theory works or not. And the idea of an EFT is, at the classical level, is kind of trivial, because you just say that I have some function f of delta and I do a Taylor series expansion. And that's an expansion in terms of powers of delta. But the non-trivial power of EFTs is really the quantum field theory, summing renormalization group logs, calculating loop diagrams, and so on. Otherwise, we wouldn't have the subject at all. So what is trivial at the classical level becomes highly non-trivial at the quantum level. And the key ingredient which is needed for this is what's called locality. That is, in a relativistic quantum field theory, as far as we can tell, all interactions, at least are local, in the sense that they're represented in the Lagrangian by some kind of local operator, say phi to the fourth and lambda phi fourth theory. And these are four fields at the same point x. And so what happens in an EFT is you factorize scales. The short distance interactions go into Lagrangian coefficients. Let's just say, I forgot to put local Lagrangian operators or coefficients. And then using that Lagrangian, you can calculate the long distance properties, for example, in terms of matrix elements of these local operators, or effectively, you're calculating Feynman diagrams. So all the new physics or whatever you want to put in is in terms of some local coefficients. I mean, we'll do examples. Well, the whole school is on examples on this, so I'm just giving you a brief overview. And because of the separation into short and long distances, you can also include in the EFT, for example, in strong interaction in EFTs, you can include non-perturbative effects via these matrix elements. So in heavy quark effective theory, which Matthias will discuss, you have an expansion in inverse powers of the mass of a heavy quark. So typically this is applied to B physics, and then MQ would be the mass of the B quark. And your Lagrangian has various operators with coefficients which are a perturbative expansion in alpha S renormalized at MB. So these, if you want, are short distance coefficients. You can calculate them in perturbation theory. And you get operators, and the standard operators that occur at 1 over m squared in heavy quark effective theory. So I'm not going to explain the notation. This will be discussed later, but you can kind of guess what this is. An operator B bar d perp squared B. So in the rest frame of the B quark, so V is the velocity vector, so in the rest frame, V would just be 1, 0, 0, 0. That is, the B quark's not moving. Its velocity vector has a time component 1 and no space component, and then d perp squared is basically the 3, well, because of the minus sign in the metric, it's minus the 3-dimensional part of d squared. So you get operators like this, and B bar, the matrix element in the B meson of this is a non-perturbative parameter, which is, for historical reasons, is minus 2 lambda 1. And lambda 1 is of order lambda QCD squared. So it's telling you effectively the mean, it's related to the mean kinetic energy or the mean momentum squared of the B quark and the B meson. It's some non-perturbative thing. We don't know what it is. And another one which comes in is B bar V sigma alpha beta, the gluon field strength, the B. And that's minus 12 lambda 2. So we don't know what these are, but in heavy quark effective theory, you can go and you can calculate the meson masses, MB, MB star. You can calculate decay form factors. You can calculate things what are called the inclusive decay rates, that is the electron spectrum for B to go to XE nu, et cetera. There's a whole bunch of things you can calculate. They all depend on exactly the same 2 parameters up to this order, lambda 1 and lambda 2. And because you have a field theory, when you have a lambda 1 which enters into this calculation and a lambda 1 which enters into that, et cetera, they're all the same lambda 1. They're a renormalized operator in the MS bar scheme. And so what is done in heavy quark effective theory is you take 2 measurements, use those. If you want they're wasted, you use them to get lambda 1 and lambda 2. I mean, all of this. But then everything else has a parameter-free prediction up to some corrections of order 1 over mb squared, including non-perturbative effects. And this works extremely well in B physics, and it's been used to extract both the quark masses, so MB and MC, and also matrix elements like VCB and so on, to very high precision, and it's crucial in testing the unitarity of the CKM matrix and tests of the standard model. So we don't know how to do these calculations without using effective field theory techniques. Yeah, so on the lattice, yeah, I should have said that. So on the lattice, you can calculate it, and you can compare now they're accurate enough that you can now extract them, and you can compare with the continuum extractions. And though you have to do a little bit of work because when we're doing continuum EFTs, we're looking at all of these operators in the MS bar scheme, and the lattice has what they call the lattice regulator, and then you have to, but there's a perturbative matching between the different schemes, and you convert, and yeah, so you can get that from the lattice. That's right. Now, in energetic processes, for example, in PP collisions into jets, or some energetic proton collisions, basically the cross section factorizes into something which is called sigma hat, which is called a hard cross-section, or a parton level cross-section. Say, for example, QQ bar to mu plus mu minus, you just calculate this like you would in a field theory textbook. But you can then do radiative corrections to this, for example, to order alpha S, you would put in some gluons and so on. So there's some sigma hat, which is a function of alpha S. And you get what's called a convolution with the matrix elements of the quark operators in the proton. And those matrix elements are non-perturbative elements, matrix elements, and they're called parton distribution functions, or PDFs. And so again, the EFT gives you a short distance factorization of short distance calculable hard scattering cross sections and long distance non-perturbative matrix element PDFs. And doing it this way, the PDFs are universal. So PP bar to mu plus mu minus, or PP bar to W production, or any other thing, jets. The PDFs are the same. They're the same non-perturbative matrix element. And then the short distance coefficient changes. So the whole goal of SCT and so on would be calculate this, or write down what's called this called a factorization theorem. So you derive factorization theorems, you calculate the hard part or the perturbative part in the factorization theorem, and then the PDFs are taken from experiment or global fits and so on. And one of the things which happens when you do this, let's see where my line is, okay, is you can separate, so let's see where I am, 6. You can separate scales. So for example, if you're doing B meson decay, the weak decays of B mesons, so for example, processes like this, you have MB, well, let's put there's the mass of the W, the mass of the B, the mass of the charm, the electron mass, etc. There are multiple scales which enter in the problem. And if you just naively started doing Feynman diagrams for B decays with all of this stuff in there, you get a very complicated mess. And if you start doing one-loop diagrams or two-loop diagrams, the more scales you have, the harder the problem becomes. It's basically, you get dial logarithms, you get all sorts of mess. So what's done in the B physics is you first go to what's called the Fermi theory, where you integrate out MW. So you go to this local, we'll discuss this. We go to a local operator where there's MW is no longer a physical scale on the EFT, so you sort of remove the MW, and now you go to an EFT which has MB and MC, and then you go calculate, and you might go to HQET where you then expand an MB and get rid of it, etc. And eventually you end up with one-scale problems, and then one-scale problems are much easier to calculate because the integral can only depend on the single scale, and therefore the scale dependence is given by dimensional analysis, and then you have a number in front to calculate. Okay, then point 7 is that there are EFTs sometimes make you realize that there's some hidden symmetries or not obvious symmetries in the theory which become manifest in the EFT. So for example, in the strong interactions, you have the B quark and the charm quark, and there are 4 physical spin states. There's the B quark spin up, B quark spin down, C quark spin up, and C quark spin down. And in the QCD Lagrangian, there's no symmetry between B and C or any of these spin states, etc. But when you go to heavy quark effective theory, you see that all these 4 states are related by what's called the spin flavor symmetry. And the reason is, if you have a heavy particle sitting at some point, it doesn't matter whether you call it a B or a C. It's just a point source. It's sitting there. And So all of these two things are the same, the B and the C. So that's the heavy quark flavor symmetry. And the spin symmetry arises because magnetic moments are down by 1 over m. So this is the magnetic moment operator, and it has an explicit 1 over m in front. So in the heavy quark limit, the magnetic moment, or which is proportional to the spin, doesn't couple. The magnetic moment interactions are suppressed, and so all these 4 states are related by the spin flavor symmetry. And that's where the power of heavy quark effective theory comes from. At leading order, you have the symmetry, and then the 1 over m corrections break the symmetry in a calculable way through the lambda 1 and lambda 2 pieces, and so on. Okay. And the other example would be chiral perturbation theory, where you have the light quark sector of QCD. So this I'll discuss tomorrow, has a chiral symmetry. And then you do perturbation theory. So the chiral symmetry is spontaneously broken. You get Goldstone bosons, which are the pions. And then you do perturbation theory in the quark masses in a systematic way. And that, well, that's the whole topic of chiral perturbation theory I'll discuss. So again, you're doing some expansion about m quark goes to 0, and the expansion is really in m quark is much smaller than some QCD scale. So for light quarks, you can do this. For the heavy quarks, you have the opposite expansion. Here you're expanding in m. For the heavy quarks, you're expanding in 1 over m. And so you have to combine different kinds of expansions for different parameter regions to really be able to make contact with experiment. The next point, which is one of the reasons why these things are used in practice, is that in quantum field theory, when you have 2 scales which are widely separated, like in the weak interactions, you had M or B decays, you had MW and MB, you can get radiative corrections which depend on logs of ratios of scales from one loop diagrams or arbitrary loop diagrams. They go like powers of alpha log. And even if alpha is small, alpha log can be order 1 because the ratio of these scales is a 25 or something here, and the log of that can compensate for alpha. Or you're working in the case of grand unified theories where the high scale is 10 to the 15 GeV and the low scale is the weak scale, and these alpha logs are no longer small. And fixed order perturbation theory, or this kind of perturbation theory, breaks down. And you have to use what's called renormalization group improved perturbation theory. Where you run parameters using RG equations, renormalization group equations, in the EFT. And they allow you to sum these large logs and make the perturbation expansion not in powers of this, but just in powers of alpha s to the n, which is a much better well-behaved expansion. And lastly, okay, just in time, you can, it's an efficient way to do BSM physics. So in the case of the SMEFT, the SMEFT is basically the standard model plus higher dimension operators. And you just put in all the higher dimension operators which are allowed by gauge invariance, and any new physics which is at a scale which is a bit higher than the weak scale has to reduce to this SMEFT. So you can fit to these new parameters and see, are there any parameters where the experiment says they're non-zero? And if you have some set of parameters and some pattern, you can try and then build a BSM model to explain what's going on. But it gives you a model-independent way of parameterizing new physics. Instead of having to keep calculating everything in your own model and fitting to data, you can just do one fit in terms of the SMEFT parameters. And then if you have a theory which you like, you can compare your theory calculation of these parameters to the fit and see whether your theory predicts something which works or not. Okay. Let's start all the way here. Okay, so the example which I wanted to discuss of how an EFT works is a simple case from electrodynamics, but it gives you many of the features that I mentioned over here. And that's just straight electrostatics, the multipole expansion. So imagine you have some collection of charges, and let's just say that there's some characteristic size A. There's some bunch of charges separated in some region of size A, and I go far away, and I look at the electrostatic potential. So R is going to be much larger than A. So from your E&M course, you know that the overall potential is 1 over R. And then there's a sum over all the multipoles, some coefficients, CLM, times A over R. I'll write it this way, A over R to the L, YLM of omega. The spherical harmonics, the angular momentum L spherical harmonic, the potential falls off like 1 over R to the L plus 1. So I pulled out the 1 over R explicitly. And I've just made it dimensionless by putting just some A. So A is some number of order. I just pick A to be some number of order the size. I'll come back to that. And so the expansion parameter delta I was talking about is in this problem is A over R. It's the ratio of the size of the intrinsic system to how far away you're measuring it. So you can think of A as the short distance parameter characterizing the charge distribution. And R is some infrared scale. It's how far away you are from it when you're doing your measurement. Now, already at this level, there's a prediction. Because you can go measure, you can take some big sphere and go measure the potential on the sphere and do a spherical harmonic decomposition on the surface of the sphere, just like WMAP does with the temperature distribution or whatever, and calculate these coefficients. And the prediction is that the YLM piece should fall off like 1 over R to the L plus 1. So the LM stuff falls off like 1 over R to the L plus 1. So you can measure them at some radius, and you can measure them at a larger radius and compare the two, and you can see, and you can verify whether this is true or not. So if Maxwell's equations are correct, it had better do this. So that's one check. The second thing you have is what we might call dimensional analysis in EFTs, which is we expect that if you have a charge distribution where the charges are sort of separated by distance A, and we have an expansion like this, we would expect that the CLMs are all order 1. Or if you decide not to normalize this way, but just, let's call this C twiddle LM and 1 over R to the L YLM, because after all, we don't know what A is, we're just measuring far away, then you would find that dimensional analysis tells you that C twiddle LM should go like A to the L, so that the higher spherical harmonics should have smaller coefficients, and by comparing, say, L equals 2 to L equals 3 or 2 to 1, et cetera, you should be able to at least get some dimensional estimate of the size of the charge system, even though you don't know anything about the details of the charge distribution. Third, you could get information on the underlying symmetry. So for example, if the charges were distributed at the corners of a cube, then the CLMs, well, this potential has to have a discrete cubic symmetry, and the coefficients have to have a discrete symmetry. And what that implies is that CLM is equal to 0 unless m is congruent to 0 modulo 4. And the modulo 4 is just because that's a 90-degree rotation. So if you find, for example, that your CLM satisfied this, you might infer from that that, oh, my charge system has an underlying symmetry. And that's kind of what we're doing with the standard model. We're looking at measurements, and we find, for example, that baryon number is conserved over various other quantities, and we're trying to figure out what's going on, even though we may not know the full theory. Now, if I wanted to calculate the potential far away, the first term I need is just the 1 over r term, which is just the total charge over r. If I want a more accurate calculation, I can then add in the L equals 1 states, the L equals 1 coefficients, and then I would get a 1 over r squared. And remember, r is bigger than a, so the second term is much smaller than the first one, and so on. So this is the sense in which your theory has a systematic expansion. This is my expansion, and I start by just keeping one term, then two terms, three, not two, but the one term for the first term, then the L equals 1, I have to keep the 3 m values, and then 5 for the L equals 2, and so on. And so the number of parameters is at leading order. So L equals 0, that would be 1. For L equals 1, there would be 3 more. There would be 5 more, and so on. And if you went to all orders in L, there would be an infinite number of parameters. But if I say stop at this point, I still have just a few, 9 in this case. There's a fixed number of parameters to each order. And as I increase the order, the number of parameters goes up. So this is all just illustrating the points I was making over there. And one of the points I wanted to make is we don't need to know what the scale A is. We don't, even though I wrote it this way, I could have used the equivalent expansion like this. I don't know what the underlying, the short distance scale of new physics is, because in this form, the A doesn't come in. But I expect, and this is the EFT power counting, I expect CLM to be of order A to the L. And if I see deviations from, let's say, 1 over R, so I see some structure, it doesn't look like a point charge, and the structure is my new physics in this case. By comparing L equals 1 to L equals 0, or L equals 2 to L equals 1, I can get some handle on where A is. Is the new distribution at an angstrom, 10 to the minus 20 meters? What is the scale of the new physics? Okay. So so there's a bunch of words. So now let me start discussing some stuff in a QFT. Yeah. That's right. So one example would be the analogous question to what you're saying is, suppose the standard model was exact. There would be the SMEFT, all the higher dimension operators, everything would go be 0. The coefficients would be 0. Now we have reasons to believe in that case that's not going to happen, but it's not ruled out here. So here, so there's nothing, you can apply this to the point charge. You will just find that all the other terms are gone. But that's not inconsistent. That's perfectly fine. It's a special case. I don't know, does that answer the question? Yeah. You mean proportional to R? Yeah, so E&M is telling you it has to go like this, right? So yeah, well, that's from Maxwell's equations and the fact that we can actually solve for the E&M problem. So now in QCD, you expect, right, the string tension leads to this potential in R, and that's confinement. And if you first saw it going like R, you maybe have no idea what's going on. But then, let's say you had some experience with QCD, then you would argue that, well, my E&M theory should have been non-abelian or something to get this and confining to get the linear term. So but that would kind of be a little extreme, because that would be like saying your starting point is completely wrong. So usually when we're doing the EFTs, we already know we have a starting point which we understand reasonably well, and you're trying to do more accurate calculations. Not that we're trying to come up with what the starting point is. So for example, in the case of chiral perturbation theory, okay, we have QCD, it's confining theory of quarks and gluons, but we know that the physical spectrum is mesons with pions. And so that's the input. We already start with a theory with pions. We're not trying to do quarks and gluons and then getting the pions out, which would involve solving some non-perturbative problem. Is that okay? Yeah. Okay, so let's just do, either QCD or QED. So the Lagrangian is a sum on sum over flavors psi sub r, the fermion kinetic term, and the covariant derivative is d mu plus IgA mu, and in the case of QCD, well, okay, so in the case of Q, let's just do the QED first. It would be IEA mu for QED, and it would be d mu plus IgA mu a TA for the case of QCD, but there's some covariant derivative. You have some mass terms. You have the field strength tensor. Let me just use, I guess I'll use the QCD form. And then maybe there's a topological term. GG dual. So this theory is in some sense already an EFT if you're just doing physics at say 10 GeV or something, because we've neglected the weak interaction. So the weak interactions would be like a plus dot dot dot, some higher dimension operators in the Fermi theory. And for the point of view of QCD and QED, they're higher dimension operators, but we'll just stick with the QED and the QCD part. And the parameters here are very few. So the parameters, actually, let me make one other point. So when you have a quantum field theory, you have to be able to go calculate and get finite results out, which you can compare with experiment. And so just giving the Lagrangian is not good enough. Part of the definition of the theory has to be some renormalization scheme, some way to do the integrals, some way to add counter terms and get a finite result. And basically everybody, for reasons which hopefully will become clear, everybody is using the MS bar scheme, which introduces this parameter mu. And hopefully you've seen how to do one loop diagrams and there are logs of mu's and so on. So the parameters of this theory are the coupling constant at mu and the masses at mu, and maybe a theta bar, this coupling constant. We know experimentally in the strong interactions that theta bar is less than about 10 to the minus 10, so that's the strong CP problem. This parameter theta bar could be anywhere between 0 and 2 pi. Why is it so small? But okay, I'm going to ignore that for the moment, but the parameters are these. And from this theory, we can calculate Green's functions. But these are not really the physical quantities in the theory. Green's functions depend on, when you calculate in a gauge theory, you have to fix the gauge, you have to add a gauge fixing term, and the Green's functions depend on how you do that and so on. But really from this, you can get something which is measurable, which are S matrix elements, which are gauge independent. And they're given by using, through the Green's functions, by using on-shell external particles. There's the LSZ formula, which I don't think I'll have time to do, but on-shell external particles and physical polarizations if you have external gauge bosons. So the QFT allows you to go calculate S matrix elements, and these are the things which are measured in experiments. The square of this gives you the cross section. The S matrix elements are the on-shell scattering amplitudes. Okay. Now, one thing to remember is that fields are not the same thing as particles. So in the QFT, the quantum field theory, well, field is part of the name, the Lagrangian is built up of a bunch of fields. So here there's psi of x and a mu of x. But then the physical particles are, in the way we think about scattering experiments, they're connected with one particle states which are at infinity and very far apart from each other. So you have some experiment where some things come in and some things go out, and the particle states are asymptotic states far away where nothing is interacting with each other. And the connection between the two is essentially that a field, let's just take a scalar, can create a particle with some amplitude e to the minus ip dot x. So there's some amplitude for the field to create a particle. And the LSZ formula, which I just mentioned, allows you to go calculate the S matrix for particles from Green's functions for fields. So you're given some set of Green's functions for fields, and then you can go calculate the S matrix for particles. And the important thing about the LSZ formula is that you can, as long as you have some operator which can make the particle, you can go calculate the cross section. So all you need to use the LSZ formula is that you can have some operator O of x. As long as this matrix element is not 0, you can calculate, use Green's functions of the operator O to go calculate the S matrix elements for fields. I'm sorry, the S matrix elements for particle scattering. And the reason this is important is that we can, field theory is basically just a big integral in the sense that you're calculating some functional integral of the actions with some sources. And in EFTs, as well, I think Tim Cohen will do this in more detail. I was just going to mention this in passing. When you have an integral, you can always make a change of variables in an integral. This is like in calculus. You can write phi as some function of some mu phi. That leads to the action changing. So you can make what's called a field redefinition of the action. And because the LSZ formula doesn't care whether I use the original field or a function of the original field to calculate the S matrix element, I can use a redefined action and get the same S matrix out as the original action. And trivial examples could be, you let phi be replaced by phi plus phi cubed over m. Say something like this. It's a change of variables like this. And the reason for doing this, as we'll see, is that it allows you to get rid of, sometimes it helps you simplify the Lagrangian and remove some terms. So these are what are called field redefinitions. And in unusual field theory like this, we actually have made some field redefinitions, even though nobody talks about it. So if I go look at the kinetic term, and I put some flavor label, the most general possible kinetic term can have some arbitrary coefficient KRS here. That is, it doesn't have to be flavor diagonal. I could have a U quark on this side, U bar, and then a strange quark on that side, for example. And if for the Lagrangian to be Hermitian, this matrix K has to be equal to K dagger. That is, K has to be Hermitian. But you normally never see this in field theory, and the reason is that if you have a matrix like this, you can always make a field redefinition to first diagonalize K. So this is some rotation, or well, unitary transformation. And then you do a rescaling of the fields. Basically, you rescale the first field by root K1, et cetera, and turn this into 1, 1, 1, 1. And nobody ever talks about it, but so you just start with a Lagrangian that way, where this KRS has been replaced by delta RS. But in principle, you can have stuff like this, and in the weak interactions at one loop, you can generate non-diagonal flavor non-diagonal terms, which you have to rediagonalize. But when you have higher dimension operators, there's many more things you can do. And in SMEFT, approximately half the possible operators that you might have wanted, you might have written down, can be eliminated by suitable choices of field redefinition. So that's a way of simplifying the EFT. But right now, I'm getting distracted, so let me just stick with what I have. So I have some Lagrangian. I started with this. And what my Lagrangian allows me to do is I start with my parameters m of mu and alpha of mu, and then I can go calculate, let's say, observable 1, observable 2, a whole bunch of observables in terms of 2 parameters and whatever my renormalization scheme is. And as I mentioned in HQET and so on, the same thing in this, you, let's say, sacrifice 2 measurements to extract m and alpha, and now you have parameter-free predictions for everything else. So in QED, you could calculate what's called the pole mass of the electron, which is the mass of the electron you would measure, let's say, by bending it in a magnetic field. So that's one observable. And the second would be, let's say, the Coulomb potential as r goes to infinity is, let's say, minus alpha QED over r, or E plus E minus. So start with the QED Lagrangian. At tree level, ME is just M, alpha is just alpha. But now you can do one loop corrections and so on and go work out what all of these are. And then the experimental values give you the parameters in the Lagrangian, and then I can go calculate Baba scattering, pair annihilation, Compton scattering, whatever I want. And I have parameter-free predictions of all of these. And the reason I want to emphasize this is that in a field theory, this M of mu, or this Lagrangian, really has plus counter terms. And these counter terms in dim reg go like 1 over epsilon. So if I just look at the full theory, the m's and so on all have plus counter terms. So in the Lagrangian, you have m of mu, and then m counter term, which typically is like m, the same m here. And then there will be alpha over epsilon and alpha squared over epsilon squared and alpha squared over epsilon. There's some infinite series in 1 over epsilon. And all of this together is what is called a Baire parameter, which doesn't depend on mu, but is infinite. And so Lagrangian parameters are in some sense infinite. And at least I don't like assigning too much meaning to them. It's just it's a bookkeeping device because we do not know how to calculate all of these, all of these other observables into 1 and 2. What we do know is start with the Lagrangian and go calculate everything. And this is kind of like an intermediate step where you take two observables, you put these arrows backwards to go calculate the parameters, and then you go calculate everything over here. So a lot of physics relies on deep thoughts about these bare parameters in the Lagrangian and issues of naturalness and so on. And I don't subscribe to any of that. I think it's a bit misguided. Okay, so let's see if I can. Okay, so maybe I'll just make one final comment, which is a procedure which is what is called matching. So for example, the standard model has strong electromagnetic and weak interactions. And if we are at energies which are much smaller than the weak scale, so let's say much smaller than MW and MZ, then we only have the strong and electromagnetic interactions, and the weak interactions have been in what the word uses, they've integrated out. So we have two different theories. One is the one I wrote over there. That's the lower energy theory with strong and electromagnetic interactions, and the high energy theory is the weak interaction. And the procedure of matching is compute the parameters of the low energy theory if I'm given the high energy theory. And at tree level, it's trivial. Alpha stays alpha, alpha S becomes alpha S, and all the masses stay the same. But at one loop, there are radiative corrections. Let's say this is a photon, and there's some W here, which are not present in the low energy theory. And so the parameters in the low energy theory get finite corrections. So M, a mass in the low energy theory, is the mass in the high energy theory, but then there are corrections which are some mass in the high energy theory times, let's say, alpha over sine squared theta or whatever, some possible corrections like this. And the way to make sure that the matching procedure works is you have to make sure that the physical observables, that is the S matrix, stays the same between the two theories. So you calculate some on-shell Green's function, on-shell amplitude in the full theory and the on-shell amplitude in the effective theory, and equate the two to extract the parameters. And what these corrections are doing is compensating for the fact that the EFT does not have some interactions which are there in the full theory. And it's included as a shift in the parameter. And what's crucial is that all of this stuff which you're missing in the low energy theory is short distance physics. It's governed by this high energy scale. And so it can all be put in terms of local operators. That is a shift in the Lagrangian. So it can always be absorbed into a shift in the Lagrangian. And this is coming from locality of the QFT. It's crucial for everything. Without locality, none of this would work. So, okay, I think I'll stop here and then take any more questions. Yeah. Yeah, I don't think it's something you should worry. Yeah, so, okay, I should. So I mean, I think what Tuhin's saying is that, say, ME mu. So let's call this, I'll say mu minus 0. That is a little bit below the weak scale. Is the value a little bit above the weak scale, plus you get things like ME, I'm just going to make this up, but alpha over sine squared theta W renormalized at mu, and then you can get things like logs of MW over mu or whatever, MZ over mu, things like this. So you get matching corrections which depend on the scale of the particles being integrated out over the whatever mu you're doing the calculation. And usually what you do is you do the matching at a mu of order these particles so that again, you don't get into trouble with large logarithms. But these are not the things you're worried about. You're worrying about the Higgs, right? Yeah, okay, I'll talk about the Higgs a little bit in the next lecture because, yeah, hopefully I can, yeah. So that's the thing I disagree with, but it's, okay, there's a physics issue and a words issue, which, okay, let's wait till the second part and then we can argue. Yeah. Yeah. So if the momentum changes, you have to be a little careful, but typically if you put in interactions where the momentum changes, then your HQET is not valid anymore. So HQET is valid when, okay, so what is HQET? You have a B quark, and if you think of the B quark as close to on shell, so you write its momentum as what's called MBV plus K. So if you want, and this would just be like it's like factoring out the rest mass. This, if V was 1000, this would be just an M in the energy component, and then all the interactions that are in this K part, where you think of K as order lambda QCD. And HQET arises because you're expanding in K over M, basically. You're saying this is small compared to that. But if something gives you momentum transfer, which is of order M, then this doesn't, you've broken down the theory. Now, this is not, so if you have, say for example, a B to C transition by a weak current, C bar gamma mu B, then what you can do is here's my weak current, here's the B coming in, here's the C going out. And if this is a weak interaction current, schematically with a W, I can take the energy, the large energy from here out in the W. And as long as so this is a meson, so there's some antiquark sitting here. As long as there's no large energy transfer in the hadronic system, HQET is still valid. So what's done in HQET is you introduce operators where this is a velocity v and this is a velocity v prime. And as long as all the large momentum is gone by the W, which doesn't couple to this strong interaction thing, you can apply HQET to the B system and the D system, and then you get form factors which depend on v dot v prime. So it's quite very useful for even processes like this. You just don't want strong interaction dynamics to put large momentum to these spectator quarks. Then the EFT fails. This one? Yeah. Wait, we're mixing up things, I think. So if you're doing B2S gamma, through the wave function, like that, right? Yeah. So when you do the one looping weak interactions, you in fact get that, and then you would then make a field redefinition, which would, okay, so what he's saying is the kinetic energy term, if this is S and this is B, is like 1, 1, and then this diagram introduces some off-diagonal term like that. And then you have to rediagonalize it. Yes. No, I'm doing this just to the Lagrange. Sorry, epsilon's a bad notation because I used epsilon in MS bar. So let's say C and C or something. Okay. So my Lagrangian, the loop has some finite piece, some infinite piece, but I'm making field redefinition of the Lagrangian. So the Lagrangian, this diagram has some C finite plus C infinite over epsilon, let's say, right? So the counter term is only that. So this would be minus C infinity over epsilon because the counter term is messed up. And then I make a field redefinition here. I don't worry about the finite part because the finite part's in the long distance piece, which is doing the diagram. It's the counter term in the Lagrangian which has to be rediagonalized at one loop. And these are one, so there's some alpha here. This is a one loop effect. So, but your example actually points out an important thing. When you make these field redefinitions to get rid of some of these operators, you also have to get rid of the counter terms of the operators, and the field redefinitions are infinite. And they, in fact, end up with, when you remove redundant operators in an EFT, the Green's functions you get are infinite because you've made infinite field redefinitions. But because the field redefinition does not affect the S matrix, the S matrix is still finite. We can talk in the coffee break. I mean, the penguin diagram is another example of this, which is a interesting example. Well, already in SMEFT, you put in the higher dimension operators for the new physics, and then you can keep going. So you start with SMEFT, and then you can go and do HQET or SCET and go calculate hard cross sections, including, so people have tried this, including the dimension 6 coefficients into the hard scattering cross sections and so on. And they're trying to do global fits, including all of that. So if you had new physics, it would change the extraction of the PDF because Drell-Yan and everything else would get deep inelastic scattering. Everything would get some corrections from dimension 6. So the consistent way to do the calculation is include those coefficients, go all the way through to calculating the, let's say, the DIS cross section, and then fit to data and extract stuff. Right now, there's no evidence for a big coefficient, so it's sort of a little bit overkill, I would say. But formally, that's the right way to do it.